Hey guys, welcome back to Analog Snippets. In last few videos, we have been looking at bandgap reference generator circuits, which are widely used to generate precise voltage references. Now that begs a question, does something like that exist for the current references? To set the stage, let's first look at where all we use current references. Obviously, current generators are needed for current biases. They are used as input of current mirrors. They are used as input of current comparators or input reference of current drivers. Reference currents are used to generate local reference voltages. Current sources are also used in level shifters, and you can think of many such applications. Notice that requirements of all these different current sources are not same. In some applications such as tail current of amplifiers or in the level shifter, you can tolerate particularly high variations in the current. But in some other applications such as reference generators and current drivers, you want as accurate a current as possible. So let's now come back to our original question. Does a current equivalent of bandgap voltage reference circuit exist? The short answer is no. Unlike voltages, we don't have a circuit which can generate a very precise current reference to within few percentage without any trimming. Oftentimes, currents are the byproduct of voltage reference circuits, which are further refined to fit the purpose. So let's look at some voltage reference circuits and find out what kind of current they generate. Let's start with conventional bandgap circuits. Currents in these two branches is dictated by value of R1. We know that difference between diode voltage appears across R1. This voltage is given by Vt ln N, where Vt is thermal voltage and N is a ratio between two diodes. So current into R1 will be simply this voltage divided by the value of R1. So this is the current byproduct of this voltage reference which we might want to use in our circuits. So now let's investigate the accuracy of this current. So first, the good thing, there is no term containing supply or VDD in this equation. So this current is virtually independent of supplies. But because of the presence of this thermal voltage Vt, this current has a very strong temperature dependence. In fact, we already know that Vt ln N is a Ptat voltage. So for a fixed resistor, this current is also Ptat. To get a better idea, let's compare the currents at extreme temperatures. Ratio of currents will be simply the ratio of absolute temperatures. And if our temperature limits are minus 40 C and 125 C, then this ratio is almost 1.7. So that is almost 70% increase in the current just because of temperature. And we haven't even talked about process variations. Process variations comes because of the process variation in the resistance value. For polysilicon resistors typically used in these kind of reference generators, there can be 15 to 20% variation in resistance value across process. To get a better feel, let's assume that the current at minus 40 C for the typical process is 1 microampere. So for 20% process variation, we can fill this table. So current will be largest when resistance is at minimum and current will be smallest when it is at maximum. So at one extreme, current will be as small as 0.8 microampere and for other extreme it would be as large as 2.04 microampere. And that is more than 150% increase in the current. In fact, there is a third source of variation, and that is variation of resistance itself with the temperature. In a typical process, this poly resistances reduce in value as temperature increases. This reduction can be a few percentage across the entire temperature range. So current at the higher temperature ends up being even higher. In fact, it is not unusual to expect 3-time variation between the minimum and maximum of the current generated by these circuits, especially if we include other sources of variation such as mismatches. So that sounds pretty horrible, especially if we consider the accuracy of voltages that these circuits generate. So do we really use these currents in a practical circuit? In fact, we do. Even with these large variations, these currents may be just good enough for biases in certain amplifiers. But these currents are definitely not usable for precision applications, for example, to generate the local reference voltages or the reference of current drivers. So can we do any better? In fact, we can by simply changing the bandgap topology from conventional bandgap to compensated bandgap. In compensated current bandgap circuits, we put resistors in parallel with diode branches. And since diode voltages are Ctat voltages, the current in these new resistors are Ctat currents. And when we add these CTAT currents with the original PTAT current, we get a compensated current. And as a result, what we are getting here is a temperature independent current. So here temperature variation in PTAT is cancelled by an opposite variation in CTAT. So we are essentially getting rid of that 70% increase due to temperature, which is a remarkable improvement. We still have the variation due to variation of resistance across process. But even with that variation, this current reference is good enough to generate local reference voltages. And this is because resistance used to generate that local reference voltage will have same process shift. So that process variation of resistance cancels out. Notice that now we have an additional diode voltage term in this topology, which we did not have in the previous topology. So this current also has some dependence on diode process variations, but this effect is usually small. And we also have the effect of the variation of resistance itself with the temperature. But suppose you don't have Banba bandgap in your chip. Can we do something to generate a compensated current using conventional bandgap? In fact, we can. And the circuit that we use are known as VBG over R circuit. The concept is rather simple. We already have a relatively precise bandgap reference voltage available to us. By using an high gain amplifier in negative feedback, we can force this precise voltage reference across a resistor. And we can tap this current using these PMOSes to be used as our temperature independent current references. This current will be simply VBG over R and hence the name of the circuit. Obviously, this circuit has additional design, area and power cost associated with it. But that is the price we have to pay for a more accurate current reference. Now, because of the process variation of this poly resistor, the current generated may not be good enough for some precision applications. By far the most commonly used method to improve the precision is trimming. Now, since in conventional bandgap the reference voltage is almost fixed, the only option is to trim the resistors. But if we are using this circuit with Banba bandgap architecture, then we can trim the bandgap voltage itself. One way to trim the circuit is to bring a mirrored current out as a monitor and then change the resistance till we get the desired current. But this will of course have the error due to a mismatch in the current mirror itself. For a more accurate trimming, this resistor is accessed directly by the tester. Amplifier is off. We force a known current into resistor and then measure the voltage. And then we adjust this resistor till we achieve the desired value. This method still have the error associated with amplifier error, for example amplifier offsets. Okay, so we got rid of temperature variations and then we got rid of process variations. Now what about the variation of resistance itself with the temperatures? For some extreme precision application, this resistance can even be an off-chip precise resistor. And by doing that, we also get rid of the trimming step. But the price we pay for this precision is an additional pin and additional BOM cost. A simple way to compensate the temperature dependence of resistance is to add an opposite dependence on the bandgap voltage itself. But the most we should expect is a first order cancellation. Now some foundries offer 0 TICO, temperature coefficient, resistors in their device offerings. These are special devices and require additional masks. Now even these resistors have process variations, so it still need trimming, but the temperature dependence is pretty small. Now so far we have been focusing on reducing the variation in our current. But there can be a situation where we want to deliberately introduce some variation in the currents. And one such example is constant GM current biases. GM is perhaps the most important design parameter in amplifier design. For example, it sets the amplifier gain, bandwidth, and noise performance. If we assume the input diff pair to be in the strong inversion, then GM is given by this equation. If we assume the ID to be temperature independent, then only other parameter to have strong temperature dependence is μn. As temperature increases, μn reduces. As a result, if we bias our amplifier with constant current, then GM reduces with increasing temperature. And that is not ideal. We would like GM to be independent of temperature. Now to compensate for the reduction of mobility with the increasing temperature, one can employ the PTAT current generated by conventional bandgap to bias the amplifier. And indeed in some cases it may well be what we need. But this cancellation is not perfect. A class of circuit known as constant GM bias can do better than that. To understand the basic concepts, let's consider this simplified circuit. Let's consider two NMOSes with width of one being n times larger than the other and both biased at the same current. There is a resistor RB at the source of larger NMOS. Let's ignore body effect and channel length modulation for this analysis. Voltage across RB is simply the VGS difference between N1 and N2. And for identical threshold voltages, it's simply the difference between their overdrive voltages. Now let's express these voltages in terms of their currents. Now here we are assuming both transistors are in strong inversion saturation. We can further simplify this equation. Okay, so now if we look at this equation, we can identify this term as the GM of transistor N1. So let's further simplify this equation. Okay, so this is the equation that we were looking for. This equation contains only a device ratio terms N and a resistor RB. So there are no supply or temperature dependent effects. There is still a process dependence because of the RB, but this process dependence is not MOS process dependence. So it still may require some resistor trimming. Now, we cannot just force any current and expect this circuit to work. This is rather more like our bandgap circuits, where we have replaced our BJTs with our MOS transistors. This circuit works only for a particular current depending on the value of RB and the ratio N. So let's look at a couple of schemes to replace these current sources. The simplest way is to replace it with a current mirror, making this whole circuit rather like a current conveyor. In general, this scheme works, but there are some drawbacks. For example, PSR of this circuit is not particularly good. And by the way, just like bandgap, this circuit also requires startup. We can always cascode these pair to improve the performance, but this costs more headroom. Other popular method is to use amplifiers. This of course requires more area, more power and more design effort. Body effect in the NMOS can be another source of non-ideality. So we can use either isolated P-well transistors, or we can flip around and use PMOS as our main transistors. And this is all what I wanted to discuss in this video. I want to end this video with some food for thought. As we discussed, this is one of the topologies for the constant GM circuit. The question is, do we have to keep the diode connected connection in this way? What happens if we flip the connections around? Does this circuit work? Give it some thought. It's quite interesting circuit to analyze. And that is all I have for today. So post your comments below and thanks for watching.